Hello there. Not all transformations are straightforward, and that's why we're going to practice with this problem. First, I'm going to just deal with the pre-image, plot those points. The page is going to get very cluttered on this one, so I'm not writing down the coordinates of -4, 0, and -3, 5 for these, but I suggest that you do so. And connect them from the triangle, and I'm going to figure out the lengths in this triangle. For AB, I'm going up 5 over 1, so that's a distance of root 26. BC is 3 by 3, will eventually become 3 square roots of 2. And this last one is going over 4 up to root 20, which eventually becomes 2 root 5. Okay, now I'm going to draw the that is the pre-image. Now I'm going to draw this image of that point there. Okay, there we go, connect them. And we'll start finding some distances. So doing this, a couple things dawn on me when I look at the picture. The original AB and this line for A prime, B prime, they look parallel to each other. So do these, and so do these. So it really does appear to have a scalar involved. When I worked through the distance formula, originally I had root 26, and now I have 3 square roots of 26. So it looks like it got 3 times longer. Now I can also look further within. This was going up 5 over 1, and then with the green it was going up 15 over 3. So it did scale up by a factor of 3. And I think that's going to be the same over here. This is going over 3 down 3, and this looks like it's going over, let's look here, that's going over 9, and this is also going, well, this is down 9, and that's actually over 9. So, write that out. Actually, I'm just being steadfast here. You don't, depending on the question, you may not have to actually do all of this distance formula stuff. Oftentimes it's enough to look, oh, it's going up 5 over 1, up 15 over 3 down 3 over 9, down 9. Scale factor of 3 involved. But just, if you want to be really meticulous, we're showing that this is the original distance, and it became that. This is the original distance, became that. This is the original distance, became that. There is a scale factor of 3 involved in all of these. This is a size transformation. Now this next part I'm going to do a little bit out of order from these questions. I'm going to actually jump to this XY mapping rule because I know there's a size transformation of magnitude 3 in there, and that helps me set up the basic structure. Because the scalar here is a 3, xy is going to be mapped to 3x something, comma 3y something. This 3 in there is important. But it's not just going to be 3x, comma 3y, because that would put this point, well, I'm just going to write up here where those coordinates would go if I multiplied them by 3. That top row would go to -12, -9, 0, but I need it to actually wind up at -8, -5, and 4. And the only way to do that is to add 4 onto everything. So I'm putting that down there. If I triple this, -12 plus 4 gets me to -8. 0 times 3 is 0 plus 4 gets me to 4. And this last one in here, scaled up -9 plus 4 is -5. So that works. This one's going to have a different shift. But first let's scale it. A little bit hard to see there, but it goes to 0, 15, and 6, but I need it here at -6, 9, and 0, so it looks like I'm shifting everything down 6. And here is my transformation rule. Now, looking at this, I can see readily from the rule that the scalar is a 3, and then I have this +4 minus 6. Does that mean that the projection point is at -4, 6? That seems too high. It's a little bit different, so we're going to go for that projection point now, and I'm going to get it by connecting each point on the image with the corresponding point on the pre-image. This is what I was talking about with things getting cluttered. So I'm connecting A with A prime. There's that line, and I do that for the others too. Once again, this is really hard to do on an iPad. If I doubted my coordinates at all, I could figure out the equations for these lines and then solve for their point of intersection. They're all going to intersect at the same place, and doing this on graph paper, I can see that it's a nice integer coordinate there at -2, +3. Now, how this -2, 3 is related to the shift here of +4 and -6, that's some pretty deep stuff. I'll leave that for you to ponder over late at night. The last thing for us left to do is figure out the area of both pre-image, the blue one, and image, the green one. This is getting fairly cluttered over here. I'm going to take this shape and draw it over here. There are different ways of doing this. I'm going to use a version where I create a rectangle and chop it into right triangles. So here's this scaled up version right over here, so I can work with it, and I'm going to figure out the lengths here. This is 4, then that's 5. And then I have all these wonderful right triangles. And I can figure out the area of each right triangle by using 1/2 base times height. Now the area of the whole thing, remember, is a 4 by 5, so I'm going to set up that rectangle and then subtract each of these guys. And there we go. The area of my pre-image ABC is 9. Now instead of doing this whole process again for the green triangle, the image, this was the pre-image, I can cheat because I know what the area of that pre-image was, and we had a size transformation of magnitude 3, and what that does to the area is it makes it 3 times longer, 3 times taller, so it increases the area by a factor of 9. And there we go. It's worth noting here that this is 81 not because 9 squared is 81, but not that you just square the area of the pre-image to always get the area of the image, but we had a size transformation of magnitude 3, and 3 squared is 9, and then this 9 times that 9 gets us to the 81. That just kind of came out to be that way. Alright, thanks for watching. Character and Scholarship for Life.